popularity greatly increased when there's pizza. This is wonderful. It's a great honor. I appreciate this, and I thank Mr. Davis and the math department and their advisor for the invitation to speak. This is particularly an honor because I think this is the first of the math colloquium, isn't it? Let's hope this doesn't end up being the last. We'll do our best. But it's very gracious of me to invite someone from outside the math department. I think that's really nice. But a bit daunting to know that we have some math professors in here. And we're wonderful math professors. Any one of them knows more about the topic than I do and could probably do a better job of presenting it. And that would be scary, except that they're friendly. So it's okay. We're all friends. And so then the next issue after I got this wonderful invitation, what should I talk about? It's got to be something that seems pretty important because after all, it's my one chance. We've got so many different majors in the room. And so I thought, what in the world can I possibly say? I think that was my initial response. Well, I've got to think of something to say. And so I thought, I know what I'll do. Colloquium speakers usually talk about things they know. So I'll make a list of stuff I know and pick something to talk about. And after several days, that list was still empty. And I was desperately trying to think of something that I knew that I could talk about, and I gave up on that. And I thought, well, suppose I talk about what I don't know. And that list got much longer, very fast. And so this is great. Now I have a much bigger range of things I can talk about what I don't know. And so that's what I thought we might talk about a little bit today, is quantifying what we know, and even, I think more important for our current discussion, a little bit about quantifying what we don't know. We all have, I think, a certain innate sense of that quantifying idea. If we need help fixing our car or something, so go ask George. He knows a lot about cars. Well, knows a lot about sort of implies that you're quantifying it. Or what if somebody comes up to you and says, I have this problem. How much do you know about such and such? Now, because this is probably a group of math and engineering types, your immediate thought is, I wonder in what units they want the answer. So in what units would you answer if you wanted to tell them how much you knew about something? Would you answer in Hartleys, perhaps, which is a possible unit, or in DITs, D-I-T, or in NATs, N-A-T, or maybe in bits, B-I-T? All of those are valid units of information, as it turns out. And we're interested in taking a look at the definitions of some of those things and figuring out how to quantify information. And so for that reason, let's go back and talk a little bit about playing party games. Now I'm talking about, I better be clear here, I see the average age of the audience. I'm talking about parties as they were when I was a kid. When I was a kid and a third grader had a birthday party, you didn't have to rent the ballroom at the Waldorf Astoria and have a 70-piece orchestra, or fly everybody to Colorado for a skiing weekend. We had traditional birthday parties. You got together, you set fire to the cake, you laughed and clapped while the poor birthday guy tried to extinguish it. And that was basically the fun that we had. And we played some dumb party games, usually pinning some part of the anatomy of a donkey to some other part of the anatomy of the donkey to the blind. But one of those games that might come up at a party like that was a game called 20 Questions. I don't know if any of you have ever played 20 Questions. But it's an information quantifying game. Because the rule is that you pick some poor victim. We didn't call them the victim. We were ahead of our time. We used a gender-neutral pronoun. We called them it. And we said we pick it, and the person who's it, they have to leave the room, and all of the other participants think of something or some person, and then they have to come back. It has to come back and guess which thing is being entertained as a consensus in the group. And so the rule is that you're allowed to ask 20 questions. The 20 questions have to have yes/no answers. In other words, they're what the mathematicians would call binary questions. And then from those 20 questions, you have to see if you can deduce the identity of the thing or the person. So if we were playing that game in here, let's see. I'll pick on you. Your name is? Oh my God. Renee. Okay. So let's suppose that, I'm not going to make you play the game. Oh, you can relax. I'm going to assume that I'm it, that I leave the room and everybody in here has decided that Renee is the person they're thinking of. So now I have to come back and pretending I don't know who you are, I have to figure out who you are. So here I am standing and facing this big group of people, and I, take a shot and I say, are you Renee? No. Oh, okay. Well, in that case, I didn't get any points for that one. Are you Renee? No. By the way, you do have to answer truthfully. Okay, I lost on that one too. All right? And now 18 to go, you know? But I wouldn't play the game that way. That would be a goofy strategy. That's not the way I do it at all. What I would do is I would start by looking at the population in here, and I said, let's divide the room right down the middle. So we'll just take this line right up here, and I'll ask, is Renee in this side of the room?
No.
No. Oh, that's too bad. I didn't get any points. But I did get a lot of information, didn't I? You people are out. I don't care about you anymore. And so now what I would do is I'd probably divide this half this way. And I would say, is Renee in this front group?
No.
Well, that's a question as to where I draw the line. You're a troublemaker, and I know you're not Renee. I know you're Remember, I grade your final exam. And so there may be more subjective questions on yours than the others. Anyway, the idea is that if Renee's in this front group, then I mark down a 1. Okay. But you see, I would have been just as happy if I got a 0, because that would have told me she was in the back group. So now I just have to split this group in half, you know. Is Renee in this half? Well, yes. Okay. And you see, I could keep doing that until finally I had it down to either you or you. And then I ask you, are you Renee? And when you tell me 0, I've got her. You see? Like that. Now, can I do it in 20 questions? Well, that depends upon whether in 20 questions I can divide this group in half. So I asked Mr. Davis for a quick head count before, and it turns out there are exactly 128 people here. Well, there aren't. But 128 is the power of 2. And so it turns out that 2 to the 5th is, what, 32, 2 to the 6th? So I think we're up to 2 to the 7th here. Yes, 2 to the 8th is 512. No, I went too high.
No, that's right.
That's right, that's right. 2 to the 8th is 512. 2 to the
8th is 256.
256, that's what I skipped.
Yeah.
2 to the 9th is 512. 2 to the 10th is 1024.
You
See, that's
wanted
why.
all this participation rights. Sorry
This
about
is
that.
the reason that they have to have the math professors come when they have the physicists speak. And so it's good. So what does this tell me? This tells me that I could actually do it in 7 questions for anybody in the room. Because what I could do is I could just divide the group in half 7 times. Because this power, which is called sometimes a power, or sometimes it's called an exponent, or sometimes it's called a log, but they're all names for the same thing. The base is 2 here, so 7, we would say 7 is the log if the base is 2 of 128. And we would write that. And that tells us that we can cut the group in half that many times. And we would get then a string of 1, 2, 3, 4, 5, 6, 7. I just made that up. I don't know who that is, but we can figure out who it is. 1, 2, 3, 4, 5, 6, 7 of those digits. We have to decide what we're going to call those. Computer science, there are probably some computer science majors here. Computer scientists are on the edge of functionally illiterate. If you've ever read any references written by a computer scientist or tried to understand even the display of a program written by a computer science, you know that's true. So they're a little lacking in the language skills. They decided a long time ago that what they would do is call these binary digits. And then I guess somebody who was a little stronger in the language skills probably said, that's not such a good idea, because we usually call our number systems digits because we have 10 fingers, and this isn't base 10, it's base 2. And they said, oh dear. And so they just contracted it and started calling them bits, which sounds really technically sophisticated, but it's actually a short form of an absolutely empty-headed construction. And so it's the case that these bits of information, if somebody said, what is your identity worth in this room, we'd probably say 7 bits. So what's Renee worth? How about 7 bits? And so is everybody else in the room. You know, it's popularly said that the problem with being in a large crowd is you can lose your identity. There might be a certain truth in that, but when you find it, it's worth more. If there were only 4 people in the room, right, that's only 2 bits, isn't it? 2 squared. Now Valentine's Day has passed, so this advice is a little late. But if you are out on a very romantic date and you've decided it's really time to find some way to express to this person I'm with just how much they're worth to me, you might try this approach. Or maybe not. But in any case, the idea is that the value of Renee's identity. Now, I'm not talking about her value. I'm talking about the value of the information. That's very important. We can think about a lot of English words that are pretty short, don't have a lot of information in them, but you know, that red octagonal sign with the STOP in the middle, you don't want to miss that. And so it's the case that 4 letters, 4 letters. How much information there? How many letters are there in the alphabet? 32, yes? Of course, because that's 2 to the 5th. Okay, so what that means then is there are, we'll have to add some punctuation marks, some spaces. But anyhow, if we have 2 to the 5th is 32 characters in the alphabet. If you wanted to make this difficult, and instead of thinking of a person in the room, you decided to think of an object or even an abstract concept, you know, and I had to play 20 questions, I might just go a letter at a time. I might just ask a question like, well, let's divide the alphabet in half, which happens we're around L or M or someplace. So is the first letter of the word you're thinking of somewhere between A and M? Is it in the first half of the alphabet? And you see, I could write down a 0 or a 1, depending on the answer, and then I could cut the alphabet in half again, and I could cut the alphabet in half again. And if I did that 5 times, I'd eventually get to the letter, and then I'd have the first letter, and I could write that down. Now, if you're thinking of the word cat, I'm going to be doing fine. If you're thinking of the word rhinoceros, I'm going to have a little more trouble. But you figure that what's the information content? That's a phrase I haven't actually used yet, but you probably should in some place. What's the information content of a single letter of the alphabet? It's about 5 bits. And so, what's an English word? 5, 6 letters on the average? So we're talking 25, maybe 30 bits. If you're a computer person, you probably like to group your bits in 8s. 8 bits is usually grouped together. I need one more to make this. There we go. Now I have 8 bits, and that's what's usually called a byte, for reasons no one really seems to know. The theory is that probably originally it was something like this: bit 8, and got shortened to this. And then somebody said, you better not do that because people will confuse it with bits. And they said, all right, B-Y-T-E. I told you about computer scientists and language. So anyhow, we ended up with a byte. But so help me, half a byte, 4 bits is called, where are my computer science students? It's a nibble. Yeah, it really is. Half of a BYTE is a nibble. So this notation may not make a lot of sense. But if we figure 5, 6 letters in an average English word, we're talking 25, 30 bits. We could divide that by 8, I suppose, and say maybe 4 bytes. Now, of course, you do realize that if I'm talking about guessing, something that you're thinking about by guessing a letter at a time, the algorithm I'm using is about as primitive as it can be. I'm not taking into account anything about, say, the frequency with which letters occur in English. They don't occur with equal probability. I could certainly improve my guessing algorithm. And if I guess the first letter after cutting the alphabet in half lots of times, and you said, yes, indeed, you're right, the first letter is Q, I don't think I'd start the process all over again for the second letter. I think I'd probably, how about you? Let's try that and see if that works as the next letter. And so that's called, by the way, data compression. And so that's basically the way data compression works. You look for certain patterns and you take advantage of those patterns to actually reduce the number of bits or bytes or nibbles that it takes to store information. So we can quantify information, as I say, not paying attention to its importance just to the quantity of information that it represents. I've taught a number of computer courses. I actually, in what used to be called the Computer Information Systems Department, I was an assistant chairperson there for a couple of years, and I teach computer courses sometimes for the engineers. And I've actually given the class some assignments based on this. I remember giving the class an assignment once of the saying, a picture's worth 1,000 words. Prove whether it's true or false. And these days it's so easy because you know the number of megapixels on your camera, don't you? So it's easy to figure out how many bits of information you have. And 1,000 words, well, we already figured out about, what, 5 bits per letter, 25, 30 bits per word. And so you can figure out how it compares. And of course it does depend on whether it's a color or black and white picture, because if it's a color you get a red, blue, or green pixel. A high definition television picture gives you more pixels, so that's more information. And I think you'll find that a picture's worth 1,000 words is actually a rather conservative estimate. I think you'll find it's more like 30,000 words, or even maybe a factor of 10 more than that. I remember giving an assignment once where I asked the students to go and calculate the total information content of our society. It's not so hard. I mean, it's not really necessary if I understand copyright law well, and I don't, but I understand that copyright is something we have by act of creation. So it's not really necessary that you register your copyright or deposit a copy of your work in the Library of Congress. But most authors think it's safe to do so. And so the Library of Congress, pretty good estimate. You can go online and say, how many volumes of information are there in the Library of Congress? And then all you have to do is decide, how thick's the average book, how many pages, how many words per page. We know how many bits per word. Let's figure out how much we know in our society. And that's the total information content. And I think if we were going to contact a distant alien civilization with one of our radio telescopes or radio transmitters, that would be a good question to ask right up front. To say to those aliens, could you please send us a signal and tell us the total information content of your civilization? Because if it comes back orders of magnitude less than ours, we've just succeeded in finding another welfare state, and we'll need whatever the extraterrestrial equivalent of foreign aid is. We've got somebody else to support. If it comes back orders of magnitude more than ours, we might be on the dinner menu. And so maybe that diplomatic meeting would not be such a good idea. And so it's interesting to compare the sophistication of civilizations according to how much information they actually know. But I want you to forget everything we've said, because none of that's what I want to talk about. Because that we know. And I want to talk about what we don't know. So let's talk about measuring what we don't know. That's I think, a more interesting topic for today. Suppose somebody says, what do you know about such? You could say, I don't know very much about that. And they say, well, put a number on that. How much don't you know? How much don't you know? And that's a problem that comes up a lot of times in fairly simple contexts, and then sometimes it's a very difficult thing. Let's go back to party games again. I'm tired of 20 questions, so let's play Monopoly for a while or something like that, where we have to roll a pair of dice. Let's suppose that in order to make the game go faster, since we're playing with friends and we trust them, we'll designate one person as the caller, and that person will have a tumbler, put the dice in, shake them up, roll them on the table, and call out what each player gets. And that way we can just move on the board. We don't have to pay attention to looking at the dice face. So the person does their thing, and out come the dice, and they say, 12. And you're thinking, I wonder how the dice came up. Well, you probably aren't thinking that, are you? Because if they said 12, the dice came up 6 and 6. I'm not a gambler, but boxcars. Anyway. And then they roll again, up comes 2. Snake up. Well, anyway, 2. And so it's the case that we know how the dice came up. So how much information are we missing about the dice in those cases? None. We didn't need to look at the dice. We just measured the outcome. Or I'd like to introduce a little bit of terminology. Let's say that the sum of the dice is actually called the macro state of the system. It's the big picture. It's the thing that's going to determine our move in the game. The exact faces on the die, in each case, that's a description of the micro state of the system. And in the case of 12 or 2, the macro state determines the micro state. There's no missing information. Suppose they say 7. Now how much do you know? Not very much. In fact, quantitatively less. Because you could have a 2 and a 13, no, a 1 and a 6, or you could have a 6 and a 1, or a 2 and a 5, or a 5 and a 2, or a 4, or 4 and 3. And if you add this all, there's 6 different possible microstates that would come to that same macro state. By the way, that term microstate and macrostate is a little weird for dice. It's better in physics where we talk about the air pressure in the room. We measure the pressure and the temperature. But we understand that because of the atomic theory of matter, the temperature and pressure are actually related to positions and velocities for Avogadro's and then some number of molecules. And we're not paying attention to the microstate of all of those particles. And we know that there are lots of different microstates, like lots of different dice rolls, that could end up with the same macrostate. The air molecules can move all over the room. If somebody opened the door and looked in here, walking by in the hall, they'd say, oh, the attendance at the math colloquium was good. Now, if they walked down the hall, I blew a whistle and asked everybody to stand up and quickly go to a different seat. And someone else walked up down the hall and said, no, the attendance at the math colloquium was good. I don't think those two people are going to stand out in the hallways. Oh, yeah, but that lady in the attractive red sweater, she changed seats. No, that's not what they're talking about. What they're talking about is just the macrostate. They don't care where the individual atoms and molecules are. And so if that's the case, with 7, we're missing more information. I'm going to try this clicker. These things sometimes work. Ah, okay. Bill Gates and I put this together. Well, and some other members of the company. And so you see what we've laid out here, just different macrostates for the dice roll and the corresponding microstates that might result, or that might result in the macrostate. I introduced another terminology too here, because what I'm assuming is that in the experimental process, what we're probably trying to do is to examine microstate variables and infer from them what the microstate of the system actually looks like. And so I went so far as to call the macrostate the hypothesis. So let's suppose that we say, let's entertain the hypothesis that the dice came up 7. Then what can we infer about the microstates? Well, this is the list. And if we assume that they're all equally probable, then we have a tough challenge here, because there's about a 1 in 6 chance that each of those microstates corresponds to that macrostate. And so there's a lot of missing information there. More missing information than there would be, for example, in association with hypothesis 4. What we would probably say is, well, for hypothesis 4, the missing information associated with those probabilities, we only have 2 possibilities, so there's a 1 in 3 chance of each one. There's less missing information there than there is if we're talking about 7 possible outcomes. 6 possible outcomes, I'm sorry, with the sum of 7. Good. I'm using a 2-letter symbol for a function that will make the mathematicians cringe. But anyhow, just to remind us that that's missing information. And that statement, I don't think anybody would say is completely ludicrous. You'd say, well, it seems at first a little strange to talk about this missing information being more or less than that missing information, but it really isn't. As a matter of fact, diagrammatically, we could probably represent a case something like this. Let me, I don't want to deal with 7, that's scary. Let's slide back to maybe 5. 5 is kind of nice, because we've got a variety of microstates, but not too many. And so let's assume then that what we do is we say, well, let's take as our hypothesis. The notation that's very often used is this kind of thing. And we mean by that the probability of A given hypothesis B. So assuming that B is right. If you demand it's right, I guess it becomes a postulate, not a hypothesis. If you think it might be right, it's a hypothesis. So anyway, if we assume B, the question is, if B is the hypothesis that the sum is 4, then basically what we would say is, well, as far as the various things we can infer from that, I think I wanted to do 5 because I want more possibilities. I want 4 possibilities. And so let's do 5, and I think I did that on the notes that I gave you. We have 1 and 4, and we have 4 and 1. We have 3 and 1, or maybe I should write this as 1 and 4, 4 and 1, 2 and 3. I'll put them in that order, and 3 and 2. And so we have A1 and A2. You know, I said I put that on the notes. I don't think I did, but fortunately, one more time, Bill Gates and I inspired us to do something with the diagram for that. There we go. This is a much neater version of the thing I'm trying to scroll on the board here. I said to my office mate when I came down, I said, I know there's going to be a misprint somewhere. Do I look at it and find it now or find it while I'm talking? So far, I think we're okay. Yeah, but sing out if you see something that isn't right. I'm old-fashioned. I go over and point to the screen. See, I can go over here and grab this mouse and do the same thing, probably more effectively. But anyhow, the sum is 5. So these are the 4 possible things we could infer if we were given the information that the sum is 5. And of course, I've associated a probability with each one, because what I've said here is, well, if the number of inferences is 4, all I have to do is to take 1/4, 1/4, 1/4, 1/4, and smear the probabilities out evenly. And if somebody said, that's a distribution, how much missing information is associated with that distribution? Using the notation like you were using before, I'd probably say, well, I guess the missing information associated with that is 1/4, 1/4, 1/4, 1/4. That is, the amount of missing information depends on that set of probabilities, or to use maybe a better mathematical term, the missing information is a function of those probabilities. By that we mean, for this particular set of probabilities, we really deeply believe the amount of missing information that would be different if the probabilities were different, if there were different numbers of them, and if they had different values. And so maybe we feel better writing that down, though it doesn't really say anything. But suppose somebody comes along and says, well, that's one way of looking at the distribution. But what if instead of that, what if you looked at it as a two-stage process? That is, what if you said, given the hypothesis B, let's say that what might happen is A1, that is maybe over there, 1, 4, or A2, or A3. I'm using this little inverted caret, this little V to mean or. In mathematics, it's called a symbol for a relation which is called disjunction. But if someone said, maybe the outcome turns out to be A1 or A2 or A3 or A4, that's after all another way of looking at exactly the same thing. And so if we take this out to its logical conclusion and we say, let's suppose that this turns out to be the correct inference, that the real result of the dice spaces are actually in this set, then we would break these out and say, all right, now we still have to decide, is it A1, is it A2, or is it A3? I think our life is much easier down here, because if this turns out to be right, then we know that we're dealing with A4. And if someone said, throw some probabilities at that, I'd probably say, well, if we are talking about events that are equally likely, this is more likely than this because this has 3. And so I would say the chances of this are only 1 in 4. But the chances of this are 3 in 4. And then starting here, any one of these is just as likely as the others. And so if I know this, I have a 1 in 3 chance that this is the correct inference, 1 in 3 chance that this is, and so on. This one's a really nice one because I have certainty, don't I? It's a 100% chance that that one's right. And for people who know about probability theory, they would say, well, let's see, this is kind of an and sort of thing, because to get here, you have to get this and you have to get this. And usually when we say the word and in probability, we end up multiplying. And it's comforting to see that if you take 3/4 and multiply by 1/3, you do get 1 in 4, which is just what we said was the chance of each of those inferences before. By the way, Bill and I have again risen to the occasion. And so what I'm suggesting here is a diagram in which we divide the possible inferences into groups. And you see here's group 1 that has 3 things. G1 is actually just a symbol for 3. And here's group 2, it only has 1 thing. This notation is called cracking a peanut with a slow chamber. It really is overly done for such a simple case. But we need to make a point here. The probability that we end up with this as our next node in the diagram is G1, the number of things in the group, divided by the total number. And we said 3 out of 4. And likewise here for P2. There's a 1 in 1/4 chance that we go to this node and then ultimately end up inferring that. So now the question is, if somebody presented us with that diagram, instead of the one that we had before, where we wrote down that nice notation, what notation would we actually write down to describe the missing information now? We'd probably say, well, let's see what we would do. We'd first have to get either here or here. And so there's a certain amount of missing information there. It would be a function of the probability 3/4 and 1/4, because those are the probabilities for the first branching that I do. And then when I get to the node, I may or may not be at the end of the game. The bottom track I kind of am. But in the top track, there's still more missing information, because I still have to decide how to characterize the missing information associated with those probabilities 1/3, 1/3, 1/3. And so I said, there's more information missing than this because I'm not there yet. There's also the missing information associated with 1/3, 1/3, 1/3. And actually, although this is kind of a moot point, I might perform just write down the missing information associated with 1, but we all know the missing information associated with 100% probability is 0. But there it is anyway, just so it doesn't get slighted. And this is absolutely not right. And the reason this is not right is because I've treated these two contingencies equally. But they're not equally likely. And so if I really want to get a meaningful mix, what I'm going to have to do is, the probability people will call this the expected value, or if you're a physics probability person, you'll probably call it the expectation value, but it's basically a weighted average. What I need to do is I need to weight these things. No matter what route I take, this has to enter the calculation. This may not, but there is a 3 out of 4 probability that it will. And the probability for this one is 1, which, as I say, it's not 1, I'm sorry, it's 1 in 4. Is 1 in 4, which, as I say, is not going to contribute anything because the missing information here is 1. And so what I would probably say is, associated with that diagram, I have a certain missing information corresponding to this distribution. A 3/4 chance of ending up like this, and a 1 in 4 chance of ending up like this. But here's the punchline. The amount of information we're missing about the dice phases can't depend on how we draw some diagram. It's got to depend on the experiment of rolling the dice. So in our heart of hearts, I think we believe that these two answers have to be the same. That the missing information associated with this distribution has to be the same as the missing information associated with this distribution, because they're the same distribution, they're just diagrammed differently. Or if we wanted to get a little more carried away, we could say, well, suppose we make it simple. Break this up into 2 groups, the purpose being that each of the groups now has the same number of things. And that makes the probabilities real easy, because if there are n groups, in this case n is 2, the probability of each group is just 1 over n as long as the groups contain the same number of things. And so we could go through the assignment of probabilities and say, well, the number of things in this group determines these probabilities. 1 over g in each case is 1 over 2. And there are 2 things in this group. 1 over g is 1 over 2 in each case. And once you've gone through a few of those, you're ready for the big one. And so the big question is this. Let's suppose that we have n possible inferences. We're going to assume it's an exhaustive set. By that I mean nothing can happen that isn't counted among those n things. We're not going to let the dice land on their edge or anything. And they're mutually exclusive, which means if one of them happens, the other can't. And so it's the case that if we have n mutually exclusive things in an exhaustive set of n inferences, and we break them up into n groups, where there are, say, G1 things in the first group, and G2 things in the next group, and G3 things in the next group, and so on, all the way down to the nth group where there are G sub n things, then how would we write the description of the missing information? And so, with that in mind, I think rather than make any attempt at that drawing on the board, I'll go to the one I did in the quiet of my own dining room with a cup of coffee. Actually, this one took 2 cups of coffee, I think. And so you'll find that I'm not so good at typing, so it may not be exactly evenly spaced. But this is the sort of thing I'm thinking about. Let me go over and wiggle the mouse. I feel like it's time to wiggle the mouse. There's a little step here, and you know I'm going to fall flat on my face. So don't be alarmed when that happens. I bounce. Anyway, there are n groups. G1, group 2, there's down here. Group 2 should have been in here, but there just wasn't room. I found that out halfway through the cup of coffee. Anyway, down here is the nth group. And so you can see that the probability associated with this particular disjunction depends upon how many things are in that group. If I put a lot of things in that group, it's like the other example we had. It might be 3 times or 4 times more probable than another. But the idea is that here I have a bunch of things in the group, inference A1 and A2, and I shouldn't be saying and, I should really say A1 or A2 or A3, and so on, all the way up to however many there are in that group. And then the next group would start one more than that. And eventually I would have all n of them placed into one group or another. And of course for each group, since the items in the group are equally likely inferences, the probability will just be the reciprocal of the number in the group. So all of these occur with probability 1 over G1 once we get to this point. And likewise here for 1 over G2. And I hope you can understand the idea. You know, in the English department, I don't think they use an ellipsis for arrows, but anyhow, this is an ellipsis for arrows. I mean, continuing this pattern all the way down to the nth group, what will happen is each of these will occur with probability 1 over Gn until finally we get all the way down to 1 over Gn as the probability for A sub n. And then somebody says, well, let's write the missing information function for that. say knuckle markers for chalk, because that way if I make a mistake, I can just shove it out of the way. So here we go. So help me write down the missing information function for that. First of all, I know that it ultimately comes down to this. Because I could draw a diagram where they're all just splayed out. You know, I could do that. And if I were to draw that diagram, that would be the same as the missing information that I would get from any other diagram I would draw, like this one. So what would I say? I'd say, first of all, I have to get to one of those groups. And so the probability of ending up at the first group would be P1, P2 for the second group, and so on all the way to Pn. Because they're, again, groups. That's my script N there. But it's clearer on the diagram up here, I think. And then once I'm in the group, I have to add the missing information associated with the group. And in fact, weigh it according to the probability that that group is the correct one. So what I'm going to have to do is take P1 and multiply by the missing information associated with 1 over G1, 1 over G2, 1 over G3, and so on. I'm sorry, that's not right. These are all G1. I'm getting carried away. I'm not there yet. I also have to add P2 times the missing information associated with the next group, G2, and so on, and P3, missing information, all the way down ultimately to the nth group, where the missing information would be a function of these probabilities, the number of things in the nth group as a reciprocal, all the way out to the end. And that's a mess that could be made somewhat better with a little summation notation. And this you do have on your sheet, I think, of notes. And that's because if you don't get time to do all the details, you can skip along. But let me just give you the upshot of the thing. We have this missing information, P1, P2, all the way up to Pn. And then we have a summation. And that would be a summation of probabilities multiplied by a missing information function of the form GI, and so on, 1 over GI, as I starts at 1 and goes all the way to n. And so this is just a shorthand notation for adding all these. Sigma just means add them up. So it just means let I be 1, and then let I be 2, and let I be 3, all the way up to I is n, and add them up. And so that actually is the form of the missing information function that we would assume on the right is the same as this thing on the left. Some notation will make this a lot easier. Over here somewhere where nobody's looking. And we just make up a function, a definition of a function with a dummy variable, let's say x. Let's say that f of x is actually the missing information associated with a distribution like this. And of course, what I'm suggesting is that this function has x arguments, all of which are 1 over x. You see why that's a handy notation to have. This is 3 bars here. You know, mathematicians do that when they mean, because I say so. So, over here, this thing we can now just write in a much neater notation as f of n. And over here, unfortunately, I can't do anything with this because these probabilities are all different depending on how many things are in each group. So I have to leave that as it is. But my summation can be made a little easier because I can just write the summation now of pi times f of gi. Because remember, I'm going to mean by f of gi 1 over gi, 1 over gi, 1 over g. It's just a shorthand notation. But this is a lot less frightening than that, and it takes a lot less time to write. And so, I think I slipped an equal sign in here when I meant a plus. So if you look on your notes, you'll see that that's about the middle of the first page. Don't let that scare you. We're closer to the end of that. The point is, this is what we really want to know. We want to know, for a given distribution of probabilities, how much quantitative missing information is associated with that distribution. But to do that, we would need to know the form of this function. And so we scratch our heads and think, how can we find the form of that function? And it turns out that this is one of those situations in which a special case actually leads us to the answer very quickly. So let's take a special case for just a minute. I just put that thing aside. And and let's consider the special case, in which we assume, I wonder, I don't think with that clicker, maybe. Interesting to see what happens if I try to go backwards. I've been lucky so far. Let's see. Of course, now I have to decide which way is backwards. Backwards, okay. All right. This case, let's assume that all n groups have the same number of things in them. So that we don't really have a G1 and a G2 and a G, we just have a G. So we have the special case in which G sub I is just equal to some value G, that mathematical symbol is for all I. In other words, G1 is the same as G2, and so on is the same as Gn is some value G. That means that the groups are also equally probable, because they all have the same number of things. And the probability is easy to calculate because we have n groups. Each one will have a probability 1 over n. And so we can say, let's take this equation up here for this special case and rewrite it. And write f of n is the missing information associated with P1, P2, P3, blah, 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 blah. Those are all 1 over n because I have the same number of things in all the groups, or at least the special case. And then I have this interesting summation. It's the summation of P sub I times f of g sub I, but that's just f of g now, isn't it? There's no sub I because all the g's are the same. What would be the point in calling out G1 or G2 or G3 separately? But that means that I can factor this out of the sum. And so let's do that. And the reason I don't, I used to hate it when I was in class and I'd write something down and then the professor would change it. Now I think it's fine. I was wrong. Anyway, I'm not worried because you have it on your sheet. See? And so what I could do then is I could take that f of g outside if I wanted and write it this way. By the way, I call these instant notes, and you'll see between the lines you might have to make a little bit of a note about how we went from one line to the next, and that's what happens here. I just take this f of g out of the sum, but now I have to ask the probability people. What do you get if you add up all the probabilities of all possible things? That's good. That's a nice chorus. And so, this is just 1. But that means that this comes down to the statement mi of 1 over n, 1 over n, 1 over n, 1 over n, plus f of g. I'm just rewriting it before I molest it here. But we have a name for this because that fits our form up there now. And so we can call this, if we want, f of n. Oh, here, I'm trying to push that up. If I succeed, I want that on the tape. Anyway. So now what am I going to do with n? I'm going to say, look, there are a total of n inferences, but I put them in little n groups. And how many are in each group? G. Well, that wasn't an exclamation, that was the answer. So it's the case that n then is just the number of groups times g. Which means that this is f of n times g, is f of n plus f of g. Okay, my math students, what function am I talking about? Tell me what function it is, where when you evaluate the function for a product, you get the same result as if you evaluated the functions and added. What kind of a function has the property that a sum looks like a product? A log is a log, it's a log, yes? It's a logarithmic function. Again, going to a dummy variable, we know that the correct form for this function has to be something like this. I'm going to use w for the variable. Has to be of the form k ln of w. So as they say, it's an exercise for the student. Later, what you can do is put in here capital N as ng and show that this really does work out to f of n plus f of g. That's an easy thing to do for a log. And so the truth is, we do know the exact form of the missing information function for at least one case. That would be the case where all w of the inferences occur with equal probability, because that would be just f of w, but we know that what that is something like k ln. Now, what do we need to do to finish this? What we need to do to finish this is to take this form for the special case and this function and substitute it back into our general grouping case. And so to save some time, I put the details of that. By the way, I left the conclusion box empty here. You see, that's just to make sure you're paying attention. So you can write in that conclusion box that we have, well, I just moved the board. F of W is KLN of W. If you go to the next page, there are the details of substituting that back and actually solving this expression for MI. And when you do that, what you find is this. You find that MI is equal to negative K times the summation. I goes from 1 to N, P sub I, Ln of Pi. And so it turns out that if you have a distribution of probabilities, you can actually get a number for the amount of missing information. Now, as I say, the details of this are the next page and a half of the handout. And because I'm worried about the clock, I'm not going to go through those details, but you all know where I live. And if you look at them and you have any questions, I'll be glad to answer those questions. But this function, sometimes it's symbolized by MI, as I've done it there. Sometimes it's symbolized by the letter H. And we say the H function is negative K times the summation P sub I, Ln of P sub I, as I goes from 1 to N. This function is sometimes called the missing information function, or sometimes it's called the information entropy function. Let's just take a quick example and make sure that it's reasonable. I know what the math majors are saying. They're saying, what's he talking about? Math is always reasonable. If you do it correctly, how could it not be ridiculous? Yeah, but I mean intuitively reasonable. Let's think about a very special case. A very special case in which there are only two possible inferences. So I guess that would be something like rolling a 3, yes? It's got to be either 1 and 2 or 2 and 1. Of course, those cases are a little too special because those are cases where they have equal probabilities. Let's suppose we have two possible inferences, but not necessarily with equal probabilities. Then it would be relatively easy to calculate this function. All we'd have to do is to write something like this. The missing information for those two probabilities, whoops, usually we put 1 first, would be something like negative K times the Ln of P1, negative K times P1 Ln of P1 plus P2 times the Ln of P2. It's a short sum. There are only two things. But P1 and P2 are in fact not independent, are they? Because there are only two outcomes. What do we know about P1 and P2? They add up to 1. So really, we could write this as purely a function of P1. We could write it as P1 Ln of P1 and 1 minus P1 Ln of P1. Ah! 1 minus P1. Oh, don't circle the mark with your fingers. Bad idea. Ln of 1 minus P1. And so once again, asking Bill Gates for help. I did a little spreadsheet here. That's scary. Now, this is a link I have to click on, so pardon me while I run back here and try not to trip on them step. Ah, there we go. So whatever you're saying, it's okay. Anyway, you can see my data columns here. There's P1, and of course there's its complement. And if you check out my formula bar at the top, I think you'll verify that the formulas are entered correctly. I took this times its ln, and this times its ln. Oh, by the way, I just divided k to the other side of the equation. Or if you like, I called that arbitrary constant 1. What you want to look at it, because I didn't want to bother with k. And then I just dragged the formula down the column and worked out the missing information associated with different probability distributions for P1 and P2, and then graphed it. And so the question is, does the graph make sense? And if I just pull this up a little bit so we can see the whole graph here. Well, I can't quite get it all in. But look what happens if P1 is 0. What's the missing information associated with the distribution of P1 is 0? Not at all. Because if P1 is 0, P2 has to be 1. And you'll see the other end of the rainbow. If P1 is 1, P2 has to be 0. I think I said that backwards. If P2 is 1, P1 has to be U. As we go up the probability chain here, as P1 becomes more and more and more likely, and P2 becomes less and less and less likely, the amount we don't know about the system increases. What would be the worst case scenario if somebody asked you to make a prediction, there were only 2 choices and they were equally likely? And so where does this thing peak? He says, running back to the podium. Where does this distribution peak? It peaks at 0.5, because we'd have the most information missing if we had to draw an inference, and we knew we had 2 things that were equally likely. You see, that's bad. So if I say to you, what do you think are the chances we're going to have another snow day before the end of the semester? And you said, it's 50-50, I'm in real trouble. If it's 95-5, then I'm pretty sure of the outcome. And so the amount of missing information is going to peak at 50-50, and I think that's a comforting thing. By the way, you'll notice the scale's a little strange, because the peak of the graph depends upon my dividing that constant through. And we go back to the data table. That peak you see here, 0.5, occurs with a missing information level of 0.693. I decided I didn't like that, so I thought, I think what I'll do is I'll divide everything by 0.693. That will make the peak 1, which seems like a good thing to do. And so in the next data table, if we make the peak 1, now you can see it's peaking at 1. When we do our plot here, there's the maximum at 1, and so on. By the way, when you do that, you're essentially dividing by the ln of 2, which means that you're measuring the missing information in bits, because if you give that some thought later, you'll realize we just measured in log 2. If you divide by the logarithm of 10, you'll be using what are called DITs, decimal digits, or sometimes called Hartleys, or Alan Turing, famous for the imitation game, called them bands, B-A-N. And so we can measure, by the way, the original units are called nats because they're based on the natural law. And so we have those units of missing information, and the distribution seems reasonable. And so now, all the other applications that were promised, but first I have to give credit where credit's due. All of this comes from a seminal work by Claude Shannon, an information scientist, who published in 1948 a paper on the mathematical theory of communication. And so if we open that paper for just a minute and go down through it, it won't take long until you start to see some diagrams very similar and some plots very similar to what we were doing. And there's that function that I explained turns up just about everywhere. And so we certainly don't need to show that it turns up in communication theory. It comes from communication theory. But probably should suggest these other areas. Anesthesiology. I don't know about you, but I think this is a classic example of where what you don't know can help you. When I have to undergo a surgical procedure, I really don't want to know. I want some entropy introduced into my brainwaves. They call that process anesthesia. And one of the ways that they measure anesthesia and its effect and its depth is by doing entropy measures. And so you wouldn't have to go very far through. By the way, this paper is so recent that it's only in a preliminary publication form. But if we go down through this paper, it won't take us very long. Sing out when you see it, because I don't want to miss it here. Before, we saw some similar things, but I think if we go down far enough here, we'll eventually find a lot of functions that look just like what we're doing here. And you can see that the information entropy is used to measure how deeply someone's anesthetized. Climatology, you worried about climate change. Well, then maybe a paper like this, where they say that they're using entropy measures for the uncertainty in climate. How far will we have to go? There it is, that function that just turns up everywhere. Or maybe in marketing. You want to do customer satisfaction surveys. Here's a claim that based on customer satisfaction skills found, it's possible to reach aimed information through fewer questions using entropy measures. And of course, we don't have to go very far. There it is, that function that just seems to turn up everywhere. And in genetics, talk about roll of the dice. The biologists know G-A-C-T, right? Guanine, adenine, cytosine, thymine. We got them right. If you want to sequence a gene, you're going to focus on the place where the most information is missing. Gene mapping and marker clustering using Shannon's mutual information find that function that just seems to turn up everywhere. Digital photography, I skipped image processing. That's a great aspect of communication theory. And so we go down and we talk about processing digital images, and of course, I could scan down through here until we find our missing information function. There it is, the information entropy. Social science, I'm going to have more applications than time, so I have to wrap it up very quickly. But you can see here, absolute majorities imply less dispersion of votes and are a synonym of higher confidence in a particular party, reducing entropy. So if you want to study voter patterns, you might end up using that function that just seems to turn up everywhere. And if you want to do economics, you've heard about the G7 conference meeting. Well, let's find out what happens when the G7 conference meets. And if we go down far enough, there we are. There, whoa, sorry about sending you swimming here. There it is, that function that turns up just about everywhere. And a little farther down, we're in there somewhere, but we're in the G7. There were US, Canada, Germany, Japan, and so the economists use that function. In finance, think about the stock market, talk about entropy. Right? Expected return. Can entropy present some advantages? And of course, you can know if I scroll down and find that equation. Diagnostic medicine. I skipped cryptography because I think that one's probably so obvious. The author proposes here that the amount of information gained by performing a diagnostic test can be quantified by calculating relative entropy between the post-test and the pre-test. And of course, we go down here and look at that. There's that function that turns up everywhere. And now, in the last couple of minutes, I want some credit for behaving. I haven't talked about physics once, maybe once. Okay. One of the things the mathematicians are fond of saying is that in 1948, Shannon founded a new field called information theory. And that it is in the mathematical world one of the few cases where the origin of it is very clear, tied to one paper and 1 year. Sort of. But in the late 1800s, Ludwig Boltzmann, based on his confidence in the atomic model of matter, which he was a great proponent, did statistical calculations to see if he could estimate something about a quantity that had already been measured as an exact differential in thermodynamics, called the thermodynamic entropy. It turns out to be dq over t. And what he found was that he could tie the entropy of a system to the number of microstates. As I was saying before in this room, if we were measuring pressure and temperature, the microstates would be what are the individual velocities and positions of the molecules. And that was the equation that he got in the late 1800s. By the way, Boltzmann didn't fare so well. He was ridiculed widely because of his belief in the atomic theory of matter. People believed that there was no way to link micro conditions in atoms because they didn't believe they existed, the macroscopic parameters. And so the stress of all of that, plus probably some other health issues and some mental problems in general, led Boltzmann to hang himself in 1906. And if you think about the significance of that date in scientific history, that means he chose to do that 5 years before Rutherford discovered the nucleus. Just a little bit of time before Millikan measured the charge on the electron. And he never knew that he would be called the father of statistical physics. And so there's a lesson in here. Don't take that approach. There's a lot of missing information in life. And you never know around the bend what the next turn of events is going to be. And so now we have Ludwig Boltzmann's tombstone, but we don't want to focus on the date 1906. What we want to focus on instead is what's carved above his head in tribute to his work, that math function that just turns up everywhere. And so now it's time to thank very much the Math Club again for inviting me today. Thank all of you for making it possible.